All the workstations are networked to the Instron PC, which contains the Naval license and must remain on during the analysis phase. Before proceeding with the analysis, all the data files must be transferred over to the workstation. Select the ME395 shortcut, which opens up a directory of a shared folder that resides on the Instron PC. Open the term-specific folder, for this example, Fall 2021. Hold down the Control button and select the desired section folder and associated EXP file. Drag the files over to the Windows E drive. This is around 3 gigabytes worth of data, which will take a few minutes to transfer. Once the file transfer has completed, close the directory window. On the desktop, double-click the Diviz 10 icon to launch the software. If the E drive folder already appears under Workspaces, skip this section. Otherwise, click the Add New Workspace icon. Navigate to the Windows E drive folder, then click the Select Folder button. Under Workspaces, expand the E drive listing. Then double-click on the folder with your lab section number. Under Current Project, click the desired recording item in the project tree, which will load the project and display the first image in the series. Expand the digital display using the small arrow above the image. We'll add 2 displays for load and displacement. Click on the Add button at the far right. In the pop-up menu, select Device Data. Do this twice. The default is Channel 1 for load. Set both the displays to show the average value. Reassign the second device to display Channel 2 displacement. The display should now show time, load, and displacement. The image viewer is very similar to any media player. Drag the sliding cursor along the timeline and observe the associated load and displacement. Along the right side are image tools. Zoom out or in, or utilize Zoom Optimize to auto-scale the image. The Display tool allows the user to toggle visibility of the axis and color scale. Both should be enabled. The image range needs to be trimmed to eliminate any initial dead time and post-fracture period, which is all garbage data. Drag the cursor along the timeline and monitor the load to determine the onset of loading. Use the up-down arrows to slowly increment by frame. In this case, the load jumps around frame 14. We'll set frame 10 as the start frame. In a similar manner, drag the cursor along the timeline to find fracture. For this example, fracture occurs between frame 1547 and 1548. We'll just round up to 1550. Make a note of these indices. We're ready to determine the surface deformation. Verify the desired recording is selected and click on the strain icon. Set the range as determined. In this case, the range is from 10 to 1550. For the core study, set the increment to 10 to save processing time. This will provide a sufficient data set to capture a representative stress-strain curve. Next, define a mask to isolate the analysis using the provided tools. A rectangular mask will work well. Simply define the region on the surface. I'm going to delete this mask to show you another tool. The Magic Wand tool automatically draws a mask on the specimen, depending on the image contrast. Under Parameters, set the correlation mode to Relative to First. Turn on the Grid Overlay. Now adjust the subset size and notice the effect on the grid. For this application, a subset size between 30 and 50 is recommended. Verify the calculation optimized mode is set to for robustness. In this mode, the step size is automatically roughly a third of the subset size. Enable the Auto Seed tool and then toggle the display icon to view the seeding points. Under Storage, enter a descriptive name to easily identify the results. When ready, click the Start button to initiate processing of the deformation field. Depending on the number of images, the processing can take several minutes. Once processing is finished, drag the cursor along the timeline and examine the deformation field. When finished, click the back button to return to the home page. Typically, dragging the cursor along the timeline will display a color gradient of displacement. Right-click on the color scale and select from a list of variables such as strain along the y-axis. Additionally, the color scale may be changed with an assortment of options. Let's explore the plot utility in DIVIZ. Select the recently created deformation field from the project tree, and then click the plot icon. At the top, the window manager toggles between a horizontal and vertical layout. In the plot area, the plotted variables may be edited by left-clicking on the axis title and selecting the desired variable from the pop-up window. Alternatively, click on the left or right y-axis setup tool along the right column. The x-axis may be edited in a similar manner. The curve may be configured by right-clicking on any associated data point. Toggle visibility of the line or symbol and/or edit colors in the pop-up window. Click elsewhere on the plot to close the window. Additionally, a legend may be displayed along the bottom. The Grid tools toggles the visibility of the grid. Switch to the vertical layout. Strain may be measured using a 2-point extensometer or an area strain gauge. Refer to your class notes. This video tutorial will demonstrate both strain sources. Select the extensometer tool and define 2 vertical points along the gauge length of the image. The endpoints may be adjusted as desired. Clicking the dimension field opens a pop-up window that provides an alternative method to set up or tweak the extensometer. Next, click on the Sigma button to automatically calculate stress. Select the dimension field for stress, then enter the cross-sectional area of the specimen. To add a strain gauge, click on the Strain Gauge tool, then define a rectangular area on the specimen. The strain gauge behaves like a rosette and provides all strain vector components. The user may provide an optional descriptive name or label for the study. When ready, click the Start button to generate the requested variables. Edit the plot axis and notice the addition of stress and strain components to the list of available options. Feel free to explore the various plotting features offered in DIVIZ. To export the data, position the mouse on the plot and right-click. In the pop-up menu, navigate to Export and then select Export Data. Use the browser to save the data to your desktop. Provide a descriptive file name for easy identification. When ready, click the Start button to export the data to the desktop. Upon successful completion, click the Close button. Here's a sample data file opened in Microsoft Excel. A MATLAB utility is available on Canvas to eliminate all the blank rows. A typical plot from the previous analysis is shown. Unfortunately, skipping every 10th frame does not provide enough data points to calculate the elastic modulus. We'll perform a second study using an increment of 1 and focus only on the elastic region. Configure the plot to display stress or load versus image index. From this plot, identify a point sufficiently beyond the linear region. In this case, index 25 appears to be a good choice. Because we skipped every 10th frame, this point is about image 250. Return to the home screen by clicking the back button. Select the recording in the project tree, then click the strain icon. All settings remain from the previous analysis. Edit the range to the elastic region. For this example, from frame 10 to frame 250. Then set the step increment to 1. The mask and subset settings remain the same. Change the storage name to elastic region or similar. When ready, press the Start button to generate the deformation field. When finished, return to the home screen. Select the elastic region from the project tree, then click the plot icon. Set the layout as desired and click the Zoom Optimize to scale the image. As before, select the desired strain method and locate on the specimen image. For this example, we'll reuse the strain methods from the core study. An optional storage name may be entered for easier identification. When ready, press the Start button to generate the requested stress and strain values. Feel free to explore the various variable relationships using the plotting features in DeViz. To export the elastic data, position the mouse on the plot and right-click. In the pop-up menu, select Export and then Export Data. Be sure to save the data to your desktop. Name the file elastic region or something similar that will be easy to identify later. The noise floor will be used to determine the resolution error of the strain measurements. Select the noise floor recording from the project tree and click the strain icon. Determine the displacement field in a manner similar to the previous studies. This image series consists of a 1-minute recording of the unloaded static dog bone specimen. The purpose of the study is to measure the noise. Once the displacement field is generated, return to the home screen. Select the noise floor displacement field and click the plot icon. As previous, locate a strain gauge and/or extensometer on the first image. We'll reuse the existing strain methods, but let's delete the stress calculation. An optional storage name may be entered. When ready, click the Run button to process the noise floor images. Configure the plot to display axial strain, epsilon YY, over time and export the data. The variance in strain measurement is noise and defines the resolution error for all the strain measurements. To exit the DeViz software, simply close the window. Please be sure to save your data before leaving the lab today.